So welcome presenters and welcome the audience. My name is Jasmina Burek and I'm a postdoctoral associate at MIT. Here with me is Kai. Kai, please introduce yourself.
Hi everyone. This is Kai Lan. So I'm a postdoc associate at Yale University and very nice to meet you all online and welcome to the session. Thank you, Jasmina.
It is our pleasure to serve as co-chairs for the evaluations of emerging technologies with a little bit of twist because we have two extra presenters. First, some housekeeping. We have 4 amazing student presenters and each presenter will share their screen. Each presenter has 15-minute time to present, followed by 5-minute questions. You can start putting the questions under the question mark, ask button, and our presenters will answer as many as possible. So first we have Bensu Manav. Bensu is a PhD candidate at MIT. Her research interests are in community resilience, in particular natural hazard mitigation, such as hurricanes. Bensu, take it away.
Thank you very much, Jasmina and Kai. Okay, I got this. Sure. Jasmina, can you tell me if you see my screen?
Yes.
Okay, perfect. Okay, hello everybody. I'm Bensu and I'm a part of the MIT Concrete Sustainability Hub, and my PIs are Randy Chen and Jeremy Gregory. And today my presentation is going to be about how we've incorporated some community characteristics into the hurricane loss estimation for buildings, one of which is texture. And I'm going to give you an overview about another topic that's been included into this presentation as well. Starting with the Sustainable Development Goals of the UN, which a lot of people have brought up during this conference. And my presentation specifically relates to developing sustainable cities and communities, where this Sustainable Development Goals is to make cities and human settlements inclusive, safe, resilient, and sustainable. And one of the core focuses in this goal is disaster risk reduction. The US National Science and Technology Council identified 6 grand challenges in achieving disaster reduction, one of which is assessing disaster resilience using standard methods, where the current standard at the moment is HAZUS, which is a loss estimation tool developed by FEMA. And in this tool, there's various different aspects that go into developing this tool, such as information about hazards, also information about structures that are exposed to hazards, a method to compute losses using these information, and how to use this to inform communities, where the different types of data that go into assessing hazards, specifically hurricanes, would be the intensity of wind speeds and also the terrain of the neighborhood, which also affects wind loads. One thing that we're incorporating into this assessment is texture, which is a specific configuration of buildings around any building of interest within a neighborhood of interest. And then when we move on to structures, the structural characteristics are summarized by stuff like the occupancy type, building type, and whether or not a building is mitigated, which gives us an idea about how a structure is going to be performing. When converting damage or structural performance metrics into loss, we need some kind of a cost metric. And it has this cost is, it's represented through replacement cost. And for communities, though HAZUS has stuff like equations for shelter requirements or household displacement, these are purely based on the structural damage and don't really incorporate variability that can be created by demographic characteristics. So we found a way to incorporate factors about the types of households that are exposed to hazards and information about the local economy. So our overarching theme is that structures are inseparable from their community. So the performance of your building cannot be considered irrespective of the performance of the community around you. This is a picture from Hurricane Michael. And Our problem statement is that the current standard for loss estimation overlooks variabilities within communities, among buildings or among households. So my research objective has been to create a community-informed loss estimation tool for buildings, which incorporates variability that's created by texture, household characteristics, and conditions of the local economy. And in my presentation today, I'm going to be talking about texture and household characteristics specifically, starting with texture. So when we're talking about the configuration of buildings, we're talking about like how ordered or how well, how ordered it is, or how well buildings place onto like a grid kind of configuration. Where if you look on the picture on the left, we see a community with more disorder, and on the right, we see a community with less disorder. And researchers before me found through computational fluid dynamics simulations that this order and grid-like structure produces channels through which wind loads are amplified. So buildings in this type of a configuration experience wind loads that are higher than ones that are in this community. So we talked about the different aspects that go into HAZIS. All of these kind of relate to different types of data sources. So some of them relate to physical models. So for instance, modeling the wind speed recurrence or modeling the building performance depends on a physical model of these things. Some of them relate to census data, such as the distribution of the different occupancy types or the value of buildings that are exposed. And then if we want to add texture into this, we need detailed GIS information about like the building footprints and the locations of buildings. This can be combined through GIS software with like the boundaries of census tracts, so that we can go from building footprints to census tracts and like incorporate all the different information that's found on different levels, either census tract, county, region, or state. And here's an example of what the building footprints look like, where each of these little dots represent a building. And if we focus on that, these are 3 communities found in Southeast Florida, each of which have a different type of texture. We're comparing based on disorder. The northernmost one has the most disorder, and the southernmost one has the least. It's also the most dense. So we also see kind of like a correlation between disorder and density, where if we're making areas built more dense, then we also have to increase the order, and it becomes more like a crystalline grid-like structure. The colors on this screenshot are actually the maximum drag coefficients that were derived from an empirical relationship produced through these computational fluid dynamics simulations, where a white color or a drag coefficient of 2 corresponds to like the conventional drag coefficient, which doesn't consider texture effects. So this is the drag coefficient of an isolated square building. So it's only based on the shape of the building, but where there are no texture effects being included, so it corresponds to the conventional estimate. And you can see that especially in the denser areas, we're seeing a lot of buildings experience drag coefficients that are higher than conventional. Using this relationship, we conducted a regional study analyzing each building within the hurricane-prone region, which included, like, we analyzed 22 of the United States, and for I'm sorry, after analyzing each of these buildings, we kind of derived like the recommended drag coefficients, like the maximum drag coefficient, took the median to plot it on the county level. And you can see that denser areas like in Florida and Texas or in New York have pretty high drag coefficients that they're higher than conventional because of these texture amplifications. And if you're not familiar with drag coefficients, it's one of the things that go into calculating wind loads. So if we talk about things in terms of wind speeds, maybe it might be easier to like maybe conceptualize. Wind loads are X% higher than the current design code, and you can see that it can be like up to 30% higher or even more. So buildings that are found within these communities that have a darker orange coloration on this map are areas where wind loads are currently underestimated for design. And this includes 25,000 census tracts, or 71% of the census tracts that fall within this region, and 37 million buildings. So the problem with underestimating wind loads is, of course, we're running into the risk of under-designing buildings, and we're also undervaluing how important it is to design buildings to higher standards or to mitigate them. We conducted a benefit analysis of mitigating homes, applying mitigation measures such as shutters, tie downs, and other basic retrofits that could be applied retroactively. And we calculated expected annual benefits, looking at the difference between the unmitigated state and the mitigated state. This is kind of like the convention of how expected benefits are defined. And we sum these up on the state level and on the county level. So on the county level, you guys can see like which communities exactly are contributing to these sums. And on the red map over here, there's actually two values that you're seeing. The one on the top is the expected benefits of the entire state, and the one on the bottom is the additional expected benefits that we're calculating when we account for texture and account for the fact that wind loads are actually higher than the conventional estimates. And our key takeaways from this study has been that wind mitigation is undervalued. And when you look at this whole region, there is actually additional benefits of $5 billion per year for applying these mitigation measures. And using the input-output factors, we estimated that that corresponds to 1.9 megatons of CO2 equivalent impact per year, which is approximately like 3% of the emissions calculated for the annual new construction. So yeah, there's not only financial benefits that we would be gaining by applying these mitigation measures, but also environmental potential like emission reductions that are being missed out on. And then the next thing I'm going to talk about is how we're accounting for household characteristics within a loss estimation framework. Where it's pretty clear that since we're already using some things that relate to census data, it's easy to incorporate additional like census information about like demographic or socioeconomic characteristics and break things down by like the impacts for different households. Where the reference for which like household characteristics we would be looking at, we were using the CDC's Social Vulnerability Index, which is a relative ranking of different census tracts or counties based on a variety of domains, one of which is, for instance, socioeconomic status. We also have stuff about household composition and race and ethnicity and stuff relating to housing and transportation. Each of these have their own ranking, and the index is basically an average of each of these domains. But what we were using for was we were referencing it to obtain the census variables that the domains and the rankings are based on, so that we could incorporate this into loss estimation framework. So using these demographic and socioeconomic characteristics, we were simulating risk for different types of households. Right now, our case study is on the scale of Southeast Florida, but since we're using a loss estimation tool that operates on the entire United States, and also we're using census data, which is also available for the entire United States, it's pretty generalizable. It's just that it's kind of a new area that we've been getting into. So for instance, one case study that we did was we wanted to look, so we had these annual expected losses, and since we had some information about households that we were simulating, we can normalize things by household income. So we wanted to see how many households and who is actually exceeding 30% of the annual income in the next 15 years. And we estimated 500,000 households in Southeast Florida. And then we wanted to look at how, what it's like if we break these down by the characteristics. So for instance, if we didn't build these relationships between the characteristics and the types of buildings, then we would distribute these characteristics uniformly, right? So for instance, we have an estimate that 14% of households are below poverty. And then when we look at our assimilated households, among the high-risk households, 39% of them are below poverty. So they're more exposed to like the risk of exceeding the household income and repair costs. If you take a ratio between these two things, we get 2.8, which next we're going to look at each of these characteristics and what those fractions look like for each of these characteristics. And we thought that this could be used as maybe a measure of the disparity between the impacts, like how much more people are in the highly exposed category compared to their overall share in the population. And then if we look at a metric like exceeding 50% of the household income, yeah, we see less households that are exceeding this metric, but there's an increased amount of disparity between that's captured by this fraction. So our overall contributions in creating this like community-informed loss estimation tool, with accounting for texture, that has been creating a more high-resolution approach where we can simulate individual buildings without having to run, for instance, like the fluid dynamic simulations for each of them, because we have this empirical relationship that breaks things down onto the resolution of buildings level. Incorporating the household characteristics, we think we have a more complete impact assessment because we're not only looking at the economic impacts, but we can talk about more of the social impacts or social disparities that are arising. And then with the conditions of the local economy, that's kind of more of our future work. So in the next steps, we want to incorporate the impacts of or on the local economy. And that's the end of my presentation. And thank you guys for listening. And I can take any questions.
Thank you so much, Bensu, for your presentation. Let's see if we have any questions from the audience, or if somebody wants to join the podium and ask directly. So I have one question. You mentioned, so the hurricane season has started, and it's important to for the community and for the industry to listen to those recommendations. What are your thoughts on influencing the right people to move forward these elements into the code design?
Yeah. Let me think about it. So there are a bunch of institutions that are focused on buildings research, and then like how do we derive these metrics? How do we assess the performance of buildings? Like the National Institute of Building Sciences, and so they've been active in pushing for like better building codes and like enforcement and adoption of building codes more. Like more adoption across the United States. But apart from that, like recognizing that there's also social impacts, I think brings in new players into the field, such as maybe groups that are focused on more of like the social equity.
Yeah, that's fantastic. We have another question from Hesam.
Yeah.
Hi, Bensu, thank you for the presentation. I was wondering, what do you think about the GHG emissions associated with the drag coefficient incorporation in your work, or more broadly, all the environmental impact aspects? Thank you.
Yeah, so the environmental impacts, it was actually a really rough estimate at this point. It's a research that we're planning on expanding on. So I had this amount of repairs that is expected for the United States, and there is an input-output factor for the carbon emissions of residential repairs and maintenance. And for now, I just use that, but it could be broken down onto even the level of building components and the materials within buildings to have a more precise estimate of those emissions. So that's something like that's kind of new that we're getting into. Thank you for your question.
Thank you.
Awesome. Well, we'll let Kai to introduce our next speaker.
Yep. So our next speaker is Audrey Beattie. So Audrey Beattie has finished her master's degrees at Colorado State University, where she was performing life cycle and techno-economic assessment on microalgae biofuels and associated co-products. And Audrey, if you are ready, you can have the stage.
Seeing that my slides are showing, but stop me if they aren't. Today I'll be talking about a probabilistic assessment of environmental economic
Not
impact.
showing, not
Oh.
showing.
Yeah, you're not showing the slides.
Oh, thank you. Okay, now?
No, it's good.
Okay, thank you. So today I'll be talking about an environmental and economic impact assessment of biofuel from cyanobacteria. First up, I'd like to thank a couple of people. Firstly, Dr. Jason Quinn was my advisor on this work at Colorado State and supervised it. And then I also have some important project collaborators from Arizona State University and Nanogas Technologies who really contributed to the process modeling that forms the basis of this work. And then this work was also supported financially by the U.S. Department of Energy. So here's a quick outline of where we're headed today, starting with some project background. So the biofuels we are interested in today come from cyanobacteria, which are a diverse group of photosynthetic microbes. And they make a promising feedstock for biofuels because they can secrete products directly into the growth media. And then these products can be harvested without extensive damage to the biomass cells. This work specifically deals with the strain Seneca cystis, which has been engineered to secrete methyl laurate, which is a fatty acid methyl ester that can be used as a drop-in biodiesel and also as a precursor co-product. And then finally, my specific role on this project is to do sustainability assessments, which is to evaluate our economic and environmental impacts. So how much will these products end up costing and what are their respective global warming potentials? So next up, I'll get into the methods. The environmental and economic assessments I've been talking about are known as techno-economic analysis and life cycle assessment. These are both founded on a process model here at the top, and then Monte Carlo analysis here at the bottom is applied to all three of these to assess the model outcomes. And so I'll start with the process model briefly. The process model captures all of the mass and energy present in the system. So it captures all consumables, including energy such as electricity and natural gas. This model specifically models two cases because the methyl laurate can be used for two broad applications. The first one is the methyl laurate can be considered a drop-in biodiesel. And in that case, which is referred to as the fuels case, methyl laurate is sold as a fuel along with the other fuel products out of HTL, which is down here, and that is the conversion of biomass. And so all of the products coming out of the facility are sold as fuels at the minimum fuel selling price. The other case, which is called fuels and co-products, the methyl laurate is treated as just a co-product. It can be used in a broad variety of applications as an oleochemical, as a precursor, ingredient to other things. And so in that case, it's just treated as a co-product and sold for a range of values. Next up is the techno-economic analysis, which is done by overlaying economic data onto that process model that I just described. Next is life cycle assessment, similarly overlaying life cycle data onto the process model. This data is found in OpenLCA and EcoInvent, and as many of you know, EcoInvent has many impact categories, but the one I'm focused on today is the global warming potential impact category. And then finally, Monte Carlo analysis is used to assess the variability and uncertainty of input parameters. And so first, it's necessary for me to define what I mean by input variability and uncertainty in this context. Variability refers to a value range, so a value that exists within a known range, and that range is the result of a varying number of assumptions or sources. Uncertainty refers to something that is unknown. So the value, usually it's associated with more first-of-a-kind aspects of the process, but this refers to a value for which the central value is known or assumed to be something, but it has not been studied enough to be prescribed a specific range above or below. So typically in sustainability assessments like this one, variability and uncertainty is dealt with by using a scenario framework. So this graph here on the left is an example of an output for a optimistic baseline conservative framework. And so in this kind of setup, all of the input ranges are put into those bins. And so optimistic here meaning that every value is at its best case scenario. This is a little bit problematic for two reasons. First is you have to assume that all values are at one scenario, which isn't necessarily realistic. And the second one is that these don't really give us any statistical information. There is implied likelihood based on, that the fact that these scenarios usually reflect some kind of technology readiness, but you can't actually pull any statistical information. So this is where Monte Carlo analysis comes in, which replaces all of those static scenario inputs with input probabilistic distributions. And then when you run the Monte Carlo, a new value is pulled at random from each of those input distributions for each iteration and allows you to simulate as many scenarios as you would like. And this is an improvement because not only can you simulate the fact that not all variables are going to be at one single technology readiness, and it also offers statistical information on your outputs. One example of this information that we're interested in is non-exceedance probability. This is estimated from the cumulative frequency, and it allows us to make assumptions about or pull results about how close we are to certain thresholds. And that is phrased such as, what is the probability that we meet a certain minimum fuel selling price or something along those lines. Monte Carlo analysis has three main steps. The first is to figure out which input values will be given input distributions. Once those have been identified, you choose your input distributions. And then the third step is running the simulation for as many iterations as you would like. So first I'm going to show some baseline results for the TEA, for the techno-economic analysis. These were generated with the average input value for each input distribution. And so here on the x-axis, we have our two cases, the fuels and co-products. And then on the y-axis, we have our minimum fuel selling price in dollars per gallon. And here we have costs split up by modules, and this includes the annual operation costs and also the amortized capital costs. For the co-product case, you add in this co-product credit, and then we add in our fixed costs, which is CapEx maintenance, operation costs, and taxes. And so the first thing to notice here is that the growth module in green is very cost intensive. This is due to nutrient demands and the capital costs associated with the ponds. And then harvest in yellow follows it up because it is also very energy intensive because it processes the entire volume leaving the ponds. And this is an area of the facility that is kind of a first of a kind approach. This system hasn't been modeled anywhere else. And so we're working to find a more efficient solution here. The next is the LCA results, which same x-axis, but on the y-axis, we're now dealing with global warming potential. Methyl laurate harvest here in yellow now dominates because energetic demand is more impactful environmentally than it is economically. And then we take a large uptake credit for the carbon dioxide that is absorbed during the growth of the algae. And then we finally close out our boundary by adding in the combustion of the fuel. So now that you kind of have a lay of how the baseline results look, we can talk about the sensitivity analysis results, which requires, it was a one at a time sensitivity analysis, so varying each input by 50%. And the most impactful parameters are those related to fuel yield. And next we have some high impact economic parameters, followed by some energetic inputs. We did the same analysis for LCA with many of the same results. Like we saw with the baseline, energetic inputs become a bit more important. The methyl laurate harvest inputs are particularly intense, as we saw in the baseline results. And then fuel yield remains impactful. And we also have the life cycle inputs. So these are the per consumable impacts, which are uncertain and were therefore included in the sensitivity. And then we have some carbon delivery inputs. And finally, if you're particularly eagle-eyed, you would see that we have the methyl laurate market value here, which is an economic input. And that is there because we performed an economic allocation of global warming potential impacts, which I'll describe a little bit later. So the implication of these results is that parameters with 5% or greater impact, so those denoted with asterisks, were used as inputs to the Monte Carlo analysis. So these are the parameters that were given input distributions. So the first set of results I'm going to show, again for the Monte Carlo analysis, starting with the techno-economic analysis. In green, in light green, we have the fuels, and then we're adding in the fuels and co-product case. And then overlaying on top of that, we have the static scenario, optimistic, conservative, baseline framework. And so I'm going to zoom in quickly to the fuels case to explain sort of the impact of this, which is the difference between the conservative and optimistic static scenarios and the minimum and maximum Monte Carlo results. So as you can see, the conservative scenario is almost $4 larger than the maximum Monte Carlo result, and about 8 standard deviations larger than the baseline result. And what this is really showing is that these static scenario analysis outcomes that were previously thought to describe the bounds of the output is actually extremely unlikely, not impossible, but highly, highly unlikely. So next, going back to the cumulative distribution or the exceedance probability, we can estimate how close we are to certain targets, such as economic parity. And so if we set economic parity at $3 per gallon, we see that the fuels case does not meet it, and then the fuels and co-products case has a very low probability of 0.3%. If we move that target to $5 per gallon, those probabilities go up by about an order of magnitude. And so clearly, you know, these probabilities are not very high at this point, but there are some high impact improvements that we can make. The first is increasing pond productivity by about 5%, which brings the probability of meeting $5 per gallon to 67% and 74% respectively. And then an additional increase to the secreted product production ratio, another 50% increase brings those to 97.5% and 96% probability. So next we'll look at the LCA results, again starting with fuels, adding in the fuels and co-products case, and then overlaying our static scenario results. And again, like we saw with the TEA, we have these large distances between the conservative and maximum, and then also between the baseline results, which are with a very similar standard deviation between the two. And what you'll notice is that it appears that this trend reverses a bit on the optimistic side, and that's for a different reason for each case. For the fuels case here on the left, this is because of the trade-off with biocrude yield, so that is the yield coming out of hydrothermal liquefaction conversion step. When that yield increases, the fuels produced increases, and this decreases your minimum fuel selling price, but that also increases the amount of combustion that the facility is now taking on, which increases the global warming potential. When you correct for this trade-off, this optimistic value actually decreases by about 5 points to be lower than the Monte Carlo minimum. On the right-hand side here with the fuels and co-products case, this is actually due to the economic allocation used to assign impacts to the two products, and that's what I'll describe right now. So the reason we're doing this is because this is a two-product system with, and because methyl laurate is has such a wide range of applications, it's really, really difficult to prescribe what the life cycle of that product is going to look like. And so what we've done is we've split up the facility to determine the impacts of each product. And so the guidance suggests splitting up the facility based on pathways where the two products are intermingled. And so for this facility, it means that we need to split up the cultivation block, the harvest block, and the storage block. These two blocks down here only exist for the conversion of biomass to fuels and therefore should not be allocated to methyl laurate. The implication of this is that the allocated modules on this process specifically are net negative, and so the benefits of economic allocation really break down. This is the formula used to do this allocation, and we don't really need to go into it other than the fact that the allocated module has this massive carbon uptake credit that I showed in the baseline results. When you allocate that credit more to methyl laurate, so as the value of methyl laurate increases, you're allocating more of that negative credit to methyl laurate, and the fuel's impact is increasing. And so instead of producing an economically valuable co-product decreasing your impact, it actually increases your fuel's impact. And so the major implication or result of this is that life cycle allocation is really an imperfect method, and it's hypothetical at its very basis, and so it should really be performed with as much transparency as possible, and also avoided when possible. So if there is a way to fully forecast the entire life cycle of a product, then that would be a better way to go about this. And so again, we can evaluate, switching gears here, how close we are to certain benchmarks, such as the renewable fuel standard. Currently, no scenario meets this standard, but there are a couple pathways that I talked about before. The first one, increasing that productivity, brings the fuels just barely into that range, and then an additional increase to the secreted product brings the fuels up to 7%. The fuels and co-products case, as you can see, do not meet this standard, and that's again because of that economic allocation. Really just creates a floor where you can only have, it creates a very minimum global warming potential where more and more advantageous inputs do not necessarily correlate to more and more advantageous global warming potential results. So finally, we have three main conclusions. The first one being that Monte Carlo analysis is a very useful alternative for addressing variability and uncertainty and avoids that compounding effect of static scenario analysis. Second, like all other microalgae fuels, productivity improvements are very, very key for targeting certain benchmarks. And then finally, that life cycle allocation methods are really not well suited to a net negative facility emissions. And this is really just something that practitioners need to be aware of. And that's why we need to be very careful to be very transparently applying these methods. And with that, thank you all so much for listening, and thanks again to the people and institutions who supported this work.
Thank you, Audrey. This is a very nice presentation, and if anyone has any question, you can join the podium to ask Audrey about her presentation. And if currently there is no question at the current stage, I have two questions actually. So the first one is from a biorefinery operation aspect, we have been always fighting with the variations, either from the variabilities or uncertainty. So on that aspect, do you have any recommendations?
Yeah, so I think my biggest recommendation is if you if you can have some kind of data-informed input distribution for a certain parameter that you know to be sensitive, then you should be performing Monte Carlo analysis. That's what this work at least has shown, is that Monte Carlo can really help paint a more realistic portrait of system outcomes. Another note on that is that many sustainability assessments are just inherently data limited, and so often we can't really inform these probabilistic distributions. And I think one intermediate step is just applying a uniform distribution to everything. And so a uniform distribution basically means that all variables within a range are equally probable. And so even if you apply a uniform distribution to each of your sensitive variables, that still avoids the overcompounding effect because you're still pulling randomized values. And so the main thing you want to avoid is just saying everything is at its best case or everything is at its worst case, because that's really giving you these extreme values that aren't actually, painting a realistic portrait of what your system outcome is. I hope that answered their question.
Okay. Yeah, thank you. And my second question is, so I see in the system boundary or the flow diagram, there is a unit process is deautering. So can you explain more about how do you do deautering, and is there any requirement for the moisture content before the HTL? Thank you.
Yes. So the dewatering step brings the algae to 20% solids. And it involves 3 intermediate steps. First is a settler, and then is a centrifuge, and then that is followed by, this is embarrassing, I don't know if I remember the third one. I modeled the system over a year ago, but it's modeled by Ryan Davis at NREL, so I used the same dewatering system that they use. And so you can always read that process report. But yeah, and so it brings it to 20% solids. All of the dewatering is pretty low energy intensity. And a lot of previous work in the Quinn group has shown that the dewatering process has been pretty well refined, and that's at this point not really a sensitive process anymore. And so, yeah, so I really just applied the Ryan Davis dewatering system from NREL.
Okay, so I see one question from the chat from Vanilla. Hi, Audrey. How did you determine the parameter distributions for MCA? Yeah, the average and the standard deviation.
Yes. So, like I was saying, this project, like many others, are inherently data limited. And so for a couple of values, there was some data. So for example, we have a first order growth model that I was able to pull operation days from. And so that was, from TMY3 data, I was able to pull how many operation days was likely for a certain area of the United States and fit a distribution to that data. That is a rare case. What actually usually happened was I would just find what other people reported in the literature that they used. And so oftentimes I used the paper from Perez Lopez, and they had a very well detailed paper on what input distributions they used. And so I used similar distributions to them, at least underlying, and then I would apply that underlying distribution to the range of values experimentally shown by Arizona State University. And so it was kind of a combination of using data when possible and then confirming those fitted distributions with literature and what other people had used in the literature before.
Great, thank you. So
Thank you.
if there is no other questions, we can let Jasmina have the stage and welcome the next speaker.
Awesome. Thank you, Audrey. Thank you, Kai. So the next speaker is Peter Chen. He is a PhD candidate in mechanical engineering at Colorado State University, and he is currently working under Dr. Jason Quinn on the economic and life cycle assessments of algae biofuels. Peter, welcome and take it away.
Screen share okay?
Perfect.
All right, awesome. So thank you for the introduction. I'm Peter Chen. I am representing Colorado State University today. I work with Dr. Quinn, so just like Audrey, we are from the same group. And I also study the economics and sustainability of renewable algae fuel systems. The work I'm presenting today is a methodology that combines both economic and environmental metrics into a single scoring system so that we can reliably compare the viability of different fuel production pathways for algae. Before I move on, I want to mention that 2 days ago at this conference, I managed to see a presentation from Eric Tan at the National Renewable Energy Laboratory. And they actually have a very similar methodology called GreenScope, developed by the EPA. So if you get a chance to look at the recordings of this conference afterwards, you can compare my presentation with their work and see some of the similarities and differences in our methodology. I'm going to start off with my acknowledgements. I want to thank everyone up here for helping me through my work at CSU, especially everyone in the Quinn Research Group. There are too many to list, but if you search for the name Quinn in the program and look at the recordings, you'll see that we have quite a big presence at this conference. So very, very proud of everyone for contributing to this conference. I also want to thank our partners at the National Renewable Energy Laboratory, or NREL, and the Department of Energy for helping with my work and financially supporting my time at CSU. So first of all, we have to start off with the question, why are we looking at algae biofuels? Some of the main advantages of algae are that they are much more productive than conventional land crops like corn and soy. And algae can be cultivated on non-arable land, which prevents conflict of those resources with food production as well. Algae are also convenient because they can integrate with waste streams like flue gases, wastewater, et cetera, to derive carbon dioxide and nutrients to grow. However, algae production is not quite as seamless as it seems. It hasn't reached commercial viability yet. And some of the challenges in that include the high capital costs, which I would say is the main obstacle in achieving a commercialized algae systems. And because of these high costs, not a lot of research has been done on commercial scale yet. And so there's a lot of uncertainty in the data, in decision-making in terms of algae fuel production. There's also quite a few input energy requirements for algae production. I won't go into the details there, but we do have to make sure that we are producing algae in a sustainable way and not dumping more energy into the system than we're getting out through the fuels. So up here is kind of a high-level process flow diagram of the work that I'm going to be presenting today. So this is outlining some of the pathways that I've worked on, trying to look at alternative pathways for field production from the cultivation stage. So in the green, in the green box here, we grow the algae and then harvest and dewater it, and then from here we can kind of choose our own pathway. The blue pathway that I've outlined is a fractionation train, which NREL has called combined algal processing. So this is a fermentation step to extract the carbohydrates into ethanol, and then moving that biomass along into lipid extraction, where we remove the lipid fraction as fuels. This leaves behind a protein-heavy residue, which can be sent downstream to co-product production or anaerobic digestion. But in general, these protein residues are not really viable for fuel production. And so an alternative pathway in the orange is a single-step thermochemical pathway called hydrothermal liquefaction, or HTL for short. And this is convenient because it has the ability to convert whole biomass into fuels. And that includes that protein fraction, which otherwise would not be very good for fuels. A third alternative pathway, which has not really been outlined in literature yet, is a combined pathway for CAP and HTL, where we where we integrate the two processes in sequence. And so we send everything through the CAP process, and then the protein residues are then sent through HTL to kind of maximize our fuel yield out of the system. And so the question that should be asked then is, how do we decide which pathway we go down? And the answer here is going to depend on the feed that goes into these conversion systems. So in cultivation, we can choose to grow algae in either high lipid or low lipid harvesting scenarios. Conventionally, algae researchers have sought out ways to produce algae with high lipid composition. And while that maximizes our fuel yield, this causes a big hit in overall productivity of the biomass. And so this puts a lot of burden, especially economically, on the algae cultivation stage. And so algae cultivators may choose to instead settle for a harvest feedstock that may be lower in lipids, and that reduces our fuel potential, but increases our ability to produce that biomass more. And so the answer to which pathway do we take is going to depend on what composition we have in the algae. And so there's a wide range of different cultivation scenarios, and so we need to look at where we want to shift from one pathway to another. So the work that I've done is all process modeling in Aspen Plus and then interfaced with Excel. Our partners at NREL have supplied a combined algal processing Aspen Plus file, which we worked out of. In terms of the HTL pathway, I did quite a bit of literature research to kind of recreate the process model in Aspen Plus and Excel. And so I recently published a paper on commercial HTL systems that kind of lets us change some of the parameters that are otherwise fairly fixed in literature. For the economic and life cycle assessment assumptions, the key performance metric for the economics is going to be the minimum fuel selling price, or the break-even price for the product that allows us to achieve a net present value of 0 in the plant. The assumptions that we use are standard discounted cash flow assumptions for an nth of a kind plant, as we call it, which represents a mature futuristic scenario where the stated technology has been fully realized. For the life cycle assessment, I performed an attributional LCA as opposed to a consequential LCA because there's not a lot of data out there on the displacement of these kind of renewable products in the market. Although at CSU we have the tools to do a wide array of life cycle assessment midpoint impacts, the key one that I'm going to focus on today is the global warming potential. We can also look at the net energy ratio by just calculating the amount of energy flowing in and out of the system. All the LCA inputs that all the life cycle assessment work that I performed was mostly done in the EcoInvent database, was done through the EcoInvent database and then compiled in the OpenLCA software. So once we get these metrics out of the way, we run these process models and get fuel selling price, global warming potential, et cetera. We can assign a scoring system to these metrics to kind of give an overall feel of how well these systems perform in multiple objectives. And so I just have example. I call these membership functions. And so on the left, we have an example of an economic one. On the right, we have an example of a life cycle assessment one. And so the concept of this is based off the fundamentals of fuzzy logic, which is it's kind of an extension of Boolean logic in that we assign a value in between 0 and 1. So as opposed to Boolean logic, where we'd only have 0 and 1 to represent no or yes that answer a certain question, fuzzy logic allows us to fill in all those values in between and essentially give us a score for each of our objectives. So for the economic objective, for example, on the left, the Department of Energy has targeted $3 per gallon gasoline equivalent for renewable fuels. And so anything at that target or below is going to represent a satisfaction score of 1. Anything beyond that, we can assign a lower score than 1, but there hits a certain point where we just can't really accept that as a viable pathway. And so we can do this for all of our objectives, economic and environmental. And all of these are going to factor into what I call an overall satisfaction factor, or an overall satisfaction score. And so the overall satisfaction score, lambda naught, is going to be weighted by the average of each individual objective lambda, and then multiplied by the minimum, the minimum between all of the satisfaction scores. And just to give some concrete numerical examples, if a simple one here is if we have a set of objectives that get satisfaction scores of 0.4, 1, and 1, that means 2 of these objectives are going to have full satisfaction, but overall we still have to weight this overall satisfaction score by the minimum. And so we take the average and the minimum, multiply those, and get an overall satisfaction score of 0.32. Which is quite a bit lower than the maximum satisfaction score because it's weighted by the minimum here. And then just to kind of contrast, if we have a second example here that all of the objectives get satisfaction scores of 0.4 across the board, we also have to weight by the average, and so this is going to get a lower overall satisfaction score than the first example, even though they have the same minimum. And so by doing this, we can holistically assess these pathways in terms of economic and environmental viability. And there are ways to pinpoint where we need to make room for improvement in all of these pathways. So now I'm going to go into some of the preliminary results that I've generated for each of my pathways. This is combined algal processing with an anaerobic digestion pathway attached on the back end to take care of the proteins. And so here you can see the trend on the right where we vary the composition and see where the overall satisfaction scores lie. This ternary diagram shows that the maximum overall satisfaction score that we can achieve is about 0.54. And as we move further to the right on this diagram, we can see that the overall satisfaction score is going to increase, and therefore the CAP pathway is clearly going to be lipid favorable. Lipids are the most energy dense component of algae, and that's typically, again, what we've targeted in the past. So CAP is obviously going to favor lipids in this scenario. We can see as we increase in protein content, going up the right slope of this triangle here, we see that we're starting to approach like dead zones in terms of overall satisfaction, and that's largely driven by the fact that proteins are not viable for fuel production in this pathway. This contrasts with the HTL pathway, in which we see increasing protein content actually doesn't have that much of an effect on the overall satisfaction, and overall we see a wider range of viable compositions that we can feed into HTL. However, the maximum overall satisfaction score for this pathway is quite a bit lower than what we would see in CAP. And that's, I think, I'll go over this later, but this is largely driven by the cost of the HTL system. Another thing to note here is that unlike the CAP system, HTL is actually carbohydrate unfavorable. And so as we go down this left slope of the triangle, we can see that higher carbohydrate content is going to drive us into these dead zones in terms of overall satisfaction. And that's largely because carbohydrates are fairly recalcitrant in the HTL reaction. They don't react into fuels quite as well as lipids or proteins. And now we can combine the CAP and HTL pathways together, and you'll notice that the ternary plot here is very similar to what we would see in the CAP and AD pathway. However, we do see a kind of a smaller range of viable compositions here, and the overall satisfaction score magnitudes are quite a bit lower than what we'd see in the CAP pathway alone. And we can compare that here. So you'll notice that the deep blue dead zones are quite a bit, have extended quite a bit in the CAP and HDL pathway. And so this is very interesting because CAP and HDL have combined have been proposed in literature as kind of a way to maximize our fuel yields. And even though we are increasing the amount of fuel that we're getting out of a CAP and HDL integrated system, the fact is that HDL is a very costly process. And so even though we have higher fuel yields in this kind of viable range of compositions, we're still getting lower overall satisfaction scores because of the high cost of HDL. And so we can break down each of these pathways by their objectives. So here I'm looking at HDL by itself, and so I've got similar plots, but these are just looking at single objectives. So fuel selling price, net energy ratio, global warming potential. These are not satisfaction scores. Just want to clear that up. And so you can see here that the trend for fuel selling price has quite a high range, and it's very dependent on the carbohydrate composition. And overall, we see a similar trend between the overall satisfaction score and the fuel selling price here. And so we can kind of conclude that the main driver for HDL viability is going to be the cost of the system, and that's why when we tack this onto the CAP system, it actually decreases the viability of the fuel production. This is kind of another way to break down each of our objectives. So I'm just looking at the best case scenarios between each of my three pathways, looking at the breakdown of the overall satisfaction scores here. And one thing to note is that I think the key thing to note here is fuel selling price, no matter which pathway we choose, is the most difficult objective to satisfy. We can see that even in these best case scenarios, we don't ever achieve that full satisfaction of the fuel selling price. And so this shows that no matter which pathway we take, algae fuels have a lot of room to, or need a lot of room to improve in terms of economic viability. So this work is not yet complete. I'm definitely, this is definitely in progress, and I'm in the middle of trying to develop more work for this. Some of the future work that I'd like to go into is, for example, to perform sensitivity analyses on other parameters besides composition. And one thing to note is that it's very difficult to it's very computationally intensive to generate these diagrams. And so it might be more useful to look in sort of these realistic ranges of compositions that we can get from cultivation, and then map these out to our ternary diagrams here, and then break down our objectives just through these more specific ranges where we would more realistically see algae feedstocks. And so for the uncertainty analysis, we can perform Monte Carlo distributions. We can generate probability density functions for all of these other parameters that have uncertainties. So things like conversion yield, feedstock price, nutrient recycle, etc. And all of these are going to be able to generate these final results for the overall satisfaction score. And this is where things are going to depend on other parameters besides composition. Another thing I want to note is that the membership functions that I demonstrated earlier were all linear, so very simple examples, but membership functions can take on basically any shape and any bounds. So something to note here is that we need to justify the shape of our membership functions, because that's going to affect our results quite drastically. We can also change the bounds depending on the current targets for economics or environmental benchmarks. So for example, in the economic target, the DOE has recently shifted to a more lofty target of about $2.50 per GGE. And so shifting this membership function over is going to, again, change our results by quite a bit. Just as an example of how of what happens if we change this membership function even just a little, I just ran a scenario where we changed all the linear membership functions into sigmoidal ones, and so what we get are fairly similar contours here, but you notice that the magnitude of all of these satisfaction scores are quite a bit lower than what we would see in a linear function. And so again, this is going to have quite a profound effect on the results, depending on what membership function shapes we choose. And this is something that we need to kind of justify, because this is a fairly subjective component of this work. Finally, I just want to go over that the work that I presented is by no means exhaustive. There's definitely potential to produce co-products out of all these pathways. Algae can create these high-value products like nutraceuticals, bioplastic precursors, and more, and that's going to help with the economics of the systems. There are also alternative fuel pathways that can utilize some other fractions that may not be viable in the pathways that I presented. So, for example, mild oxidative treatment, or MOT, is kind of a newly developed pathway by NREL that allows some of the proteins to go into fuels without having to tack on that HTL system on the back end. Meanwhile, on the HTL side, there's kind of a new development called sequential HTL, where we can extract the carbohydrates ahead of time into a high-value co-product, and then send the rest of the biomass into fuels to kind of help out with the overall fuel yield of the system and the economics. So that was quite a lot of work. Thank you all for tuning in. If you have any questions, please fire away. And I hope you enjoy the rest of the conference.
So we are running out of the time, so we will not take the questions now. Let the audience put some questions in the chat box, or if we have time in the end, and bring Peter back. Thank you, Peter. And Kai, please introduce our next speaker.
Sure. Our next speaker is Opeoluwa, Wonuola, Olawale. Excuse me if I got the wrong pronunciation. And she's the doctoral candidate of Advanced Energy System at Colorado School of Mines. Her multidisciplinary research interests focus on the behavioral pattern analysis in the USA residential demand flexibility program design. As an energy researcher studying and working with the National Renewable Energy Lab and real partnership with mines, she supports demographic studies to improve the accuracy of national residential building occupancy models in RESTA by at least 5%. Now, you can have the stage.
Thank you. Hi.
Great.
Yes, thank you. Hi, thanks for the introduction. My name is Opeoluwa Wonuola Olawale. As I said, I am a PhD student of the Advanced Energy Systems program at Mines. It's a collaborative program between Colorado School of Mines and the National Renewable Energy Laboratory. Today, I will be talking to you about who is most likely to interact with demand flexibility at home using sociodemographic predictors from the American Time Use Survey. Our goal is to identify what key demographic factors influence energy use behavior to improve residential building stock energy simulations. And these are required in our efforts towards sustainable and efficient energy systems. Today, we'll tackle three major questions to answer this question of who would most likely interact with demand flexibility at home. One is to see what it would look like to just use population statistics to predict demand flexibility behavior, and what key demographics are key and what should be included, and what, based on our framework, who utilities should target for these common demand flexibility technologies at different times of the day. So for today, I'll be following this outline, and I want you to remember by the end of this presentation that this study now allows us to explore diversity in how we will design demand flexibility programs going forward. So what's the big picture? First, what is demand flexibility or demand response, or what I'll call DF going forward? This is the ability of buildings to reduce peak demand, A, or to modify the load shapes in response to utilities requests or price signals, as illustrated in the first two figures on the left. DF also allows more renewables in the grid. In fact, up to $13 billion in annual grid costs could be avoided if only DF reached its full potential. I want you to see how human elements of grid interactive technologies play out. I want you to imagine that you finally enrolled in something like thermostat demand response. And so while you were sleeping or resting, you got a text from the utility about pausing your heater because it's critical peak period. How likely do you think you would respond or override a request? How do we tackle this problem? What if we understood our DF customers, or who is doing what the most, and what people prioritize when it comes to demand flexibility? Should there be a roster? Can we get better participation? Really, our big motivation is this. Our scope is residential buildings, a sector that consumes over 20% of electricity generated with over 135 million customers. On the left, you would see the annual estimates for electric peak demand reduction that is supposedly possible from demand response, around 40 gigawatt, while the middle figure shows the actual peak demand reduction that is achieved, less than 10 gigawatt. Throughout the different sectors. On the right-hand figure, you see that despite the millions of dollars spent on customer incentives all over the years for demand response, we have less than 40% of estimated DF potential being realized. So there are still two big issues, which is poor participation and high override rates. So really, when it comes to understanding what different people do during different periods, this is critical. And so in looking at the literature, we wanted to understand what has been done and how human elements has been incorporated into energy demand estimates over the years. We identified about 65 relevant studies, and occupant behavior remains the most difficult to represent. And so we're taking on a challenge. We also note that time use surveys are one of the most relevant to approximating occupant activities at large scale. There's a concept called energy performance gaps. These are prediction errors that have been investigated in the literature when attributing to energy demand or peak demand estimates. And EPG is mainly due to poor characterization of building characteristics. Things like weather, occupant behavior, and by occupant behavior, I really mean human interactions with the building, for example, going in or going out. Specifically, up to 300% error margin has been attributed to poor occupancy representation by Annex 66, which is the International Energy Agency on body of knowledge for occupancy behavior modeling. They explain that this is because interactions are usually random and they differ significantly from household to household. And so this further points to the importance of properly representing occupant interactions to help us improve DF program design and improving our peak demand estimates. We take a unique approach to fundamentally thinking of energy use to result from activity and equipment, where activity is kind of the behavior. Of course, social scientists argue rightly that it is not our love for energy that makes us use electricity, but the activities that we do daily. And this is what is known as the social practice theory. The current occupant behavior models that are available are stochastic-based models with expensive computational resource requirements, and most of them are like black boxes, which makes it more difficult to incorporate them into energy models. Other approaches assume just average time spent on activities on a lump. In general, demographic details are either ignored or lumped without knowing which matters more. And so it's difficult to pull across different cities and just make our energy models transferable. So put it simply, the literature and the utility industry still lack broad insights into the human components that will affect demand flexibility or human interactions with DF. So we therefore develop a framework based on machine learning regression models to delineate key demographic variables influencing occupant end use, activities, choice, and duration. And so how do we go about this? The first thing, based on the gaps in the literature, is to find what demographic variables should we even focus on and when. So first, we collected one-day data on occupant activity and timing for about 200,000 randomly selected respondents from the 2003 to 2018 American Time Use Survey, which I'll call ATUS. We use ATUS to represent the USA. And we even kept aside a test area for our model validation process. Our next major step was to identify and aggregate the over 420 activity options into 14 DF-related activities. So for the first time, we delineated things that are specific, activities that are specific to demand flexibility. For example, connected thermostats are relevant to when you're just home or sleeping, and even included pool pump use, which is something that is for the first time looking at how new emerging technologies for demand flexibility can be incorporated in our understanding. To illustrate what the ATUS looks like, here's a snapshot of a very small part of the data set. We combined 4 different files to get a full picture for each of these respondents. Of course, they fill out their day starting from 4 a.m. So here are 37 observations for about only 4 respondents with their TU case ID, where they report their start time and end time for a TR code P 6-digit code activity, and then and then tell us what they do throughout the day. So we have almost 4 million observations for these about 200,000 respondents. And then we need to aggregate this log into period chunks where we have critical peak, for instance, going from 2 p.m. to 7 p.m. and sort of gives us a DF profile activity for all our respondents. Next, we explore several demographic variables that are usually discussed in the literature, and then we focus on 17 demographic variables that are relatively easier to find in the public domain. We also control for fixed year and other effects. Then we evaluate the machine learning regression models on the probability of choice, which we call their extensive behavior. That's what they choose to do. And duration of activities, which we call the intensive behavior, how long they spend on what they choose to do. And so finally, we check for statistical significance of the selected demographic variables using post-selection inference tools. In testing the predictive models, we used separate test data that the models had not seen before. It's more like a service area that utilities or DF programs might be interested in. Our service area has 4,225 people in total, and that's what you see in orange for their probabilities of the activities on the x-axis for each activity on the y-axis across the different periods in each plot. So for instance, it is more likely to be just home, needing your thermostat on during critical peak period with a 0.24 probability, and most likely sleeping during the early hours of the morning during off-peak hours with a 0.36 probability. It also makes sense that it is more likely that cleaning activities, including taking showers, would be in the mornings during off-peak. We also notice how only few report pool use and is the least probable activity. Importantly, the choice model predictions in blue do quite well in predicting the mean probability of each activity that is related to energy end use. When we plot the percent deviation of the predicted extensive behavior using our test service area, we notice our probability predictions using population statistics to be within less than 20% error margin for each choice of this activity at a stock level. We, however, notice for computer use and laundry during off-peak period on the far right that we are off by at least 20%. We think that the tiny probabilities of doing these activities during off-peak would be the reason for this, or it could mean that both computer use and laundry choice is indifferent to who you are. So for the duration, we have the x-axis that is a 6-hour span for the average time spent per period, while the different activities are on the vertical axis. The different activities in total summarize how people use their time during the different periods. It's more like showing the day of a typical American. When we look at the time people spend on activities, we notice how the amount of time actually changes from critical peak to off-peak periods. And of course, as expected, people sleep longer at night past 7 p.m. during peak night, and shows that what we are predicting and what we are seeing is quite reasonable. But the first key takeaway is how much time is spent during critical peak period on most of these activities compared to off-peak period on the far right. So we can tell that people generally prioritize activities in the evenings between 2 p.m. and 7 p.m., which is critical peak. And ironically, this is when utilities find DF resource critical. This is telling us that this might be an explanation for why participation could be low, and probably help us to understand mechanisms to start understanding who to focus on during these different time periods. And of course, the other key takeaway from these duration models is how closely we can predict how much time people spend on these activities just by knowing their demographic characteristics. You'll notice these plots showing good predictions within the plus or minus 20% throughout. This means that we can now monitor time use differences as key demographics of a place changes. We can also apply this framework to weekday versus weekend, or for even different service areas across the nation. Next, after running the different models for each period, we extract which demographic variables have non-zero significant relationships with the choice and duration of DF activities. We looked at the top 5 significant predictors across different time periods for the different activities, ranking them by their marginal effects and beta coefficients, given that these variables have different units. We found these 13 top predictors across all the models. We can summarize these as personality, including how much time you spend alone, what your gender is, family dynamics, including the number and presence of children, the social status of whether you're employed or not, what your income is, and education, and race and ethnicity. This is how we kind of apply it to a use case. The sorting of marginal effects based on standardized beta coefficients looks like this for 3 activities during critical peak period. The focus here is on the top 5 predictors per period, and these changes with activity, as you'd notice. To demonstrate applicability to DF, let's focus on 2 common DF programs such as connected thermostats and smart water heaters. For thermostats, we choose to look at just being home and sleeping activities, while shower or cleaning activities related to smart water heater. The numbers in bold are the regression coefficients, while those in brackets are the standard errors. For instance, let's look at gender. Women sleep generally less than men by 24 minutes, which is fascinating, but 7 minutes more engaging in cleaning activities during critical peak period. So this tells us that DF would more likely get more success with connected thermostats with women, but smart water heater might get more success with men during critical peak period. Next, you look at the labor force status. It means that a person who is employed at work is more likely to respond to DR thermostat event call during critical peak period, because someone who is not in the labor force spends about 23 minutes more during critical peak. Another one that is quite fascinating is how a postgraduate sleeps by 65 minutes less on average in the evenings compared to someone with less than high school education. This means that utilities could start thinking about switching things around based on educational level and asking upfront if that might be a priority. While the mechanisms for this needs to still be tested, these results offer deeper insights into the timing and priorities for different people, unlike before. There's simply so much that we can learn about these different subgroups during different periods engaging in DF-related behavior. But now we have a basis on a quantitative basis to embrace diversity in the way we design technological programs. We tackled the three major questions on how to answer who would most likely interact with demand flexibility at home by integrating human behavioral elements into improving DF participation and peak demand reduction potential. First, we demonstrate a framework that shows that demand flexibility behavior could be predicted based on population statistics and what that looks like. We also showed good prediction accuracy up to national scale. We also found out that gender, hermit lifestyle, social status, family dynamics, education, and race are key demographic predictors after sifting through more than 17 sociodemographic factors. It also means that we have a chance to improve our energy use models or demand flexibility models that require activity prediction with fewer specified publicly available demographic variables. We also showed that there are social demographic subgroups that can be prioritized if they change their intensive behavior, even if they change their intensive behavior with each activity and by inference, each associated DF technology. So far, we showed how we leveraged and connected existing data to knowledge gaps. We also think that this is an opportunity to create roster messaging platforms for DF flexibility customers. And yes, we're still far from integrating these insights into DF estimations, but we are closer to better understanding how people's behavior could impact how we frame our energy solutions to customers. We are hoping that our work informs future messaging schedules that help demand response reach its potential. Based on the fundamental study we just completed, we have started work towards integrating these key demographics into RESTOP, for example, which are large-scale residential energy models, such that they can now be sensitive to different cities' population statistics. We also think that since the scope of our work excludes real-life studies, we think that utilities might start with some of our results in framing such message roster ethnographic studies. This study also serves as a foundation for some equity and environmental justice questions that we believe needs to be tackled, especially relating to disadvantaged communities in our energy models. Finally, it's important to caveat that we focused on unbiased energy end-use activities and did not make assumptions on the connections to individual energy end-use, as is common in the literature. Here are my references. Thank you so much for listening. These are my contacts if you'd like to reach out to me regarding our study. Thank you.
Thank you. Thank you all. It's a very nice speech, and we found a lot of interesting and meaningful information from your presentation. So if anyone has any question, you can join the podium right now. And we can have one or two more questions. Yeah, go ahead.
Hi.
Hi.
Thanks for a really interesting talk. Very thorough work. Raised a lot of interesting questions. So one I'd just like to ask about is when you were describing the validation of your analysis, you mentioned that you withheld a sort of a test neighborhood or group, estimated your models and then checked the predictions for this group against the observations. Could you talk about the strategy for that? And I think it sort of links to your point on justice. Sometimes people just sort of randomly withhold X% of the data, but you might consider withholding only the poorest or something, or only people of a certain racial or ethnic group or something like this, and seeing how these possibly undersampled populations might be mischaracterized if models are estimated on other groups. But sorry, please.
Yeah, thank you. Thanks a lot for that question. Yes, when we were doing the out of population test sample, we only took out 2%. and that was across different climate zones, and just making sure that we are looking at the population. And this is something interesting, just comparing the population and the all ATOS population and the model population. I think this was one of the most fascinating for us, that even across different populations, the behavior was sort of consistent throughout. So much so that we think the social practice theory is very true, that behavior can be consistent across different populations. But when we look at different states, for instance, when we start looking at different states, for instance, of course, the trend is still similar, but you begin to see little differences across different states. So this is an opportunity for us to start looking at maybe, for example, disadvantaged communities in comparison to maybe high-income communities. I think this study gives that framework. Yes. So yeah, this is what we did.
Thank you. And I think our time is up for 1:30. And thank you everyone again for joining this meaningful session. And we have a very meaningful discussion and communication. And also after this session, we can communicate from this platform. And thank you again, everybody, and enjoy your rest of the day and enjoy the rest of the conference. Thank you.
Thank you. Bye.
Thank you all. Bye-bye.